had. So if you were doing this challenge with the adjacency list, then it should look something like this. So let me change that text color to black. So your adjacency list should look something like this. Now recall that the individual lists inside of these lists don't have to have a specific order, so they just represent the neighbors of that node, right? So hopefully everyone can see this list right here. That's just going to be under the edges and everything. Okay, so any questions? So now that we can store graphs effectively in our program, we can start looking at graph algorithms. And our first goal is to traverse the entire graph. And that means to start at some node and visit every other node in the graph. And so, for example, if I had a graph with a lot of nodes, and I had edges like these, to traverse the graph means I start from some node, so like this node here, and then I visit this, and this. Now, it doesn't mean that I have to use every single edge in the graph. It just means I have to visit every single node. And keep in mind that today we're only going to be dealing with graphs that are connected. So that means that there won't be just random nodes out here that we won't be able to visit by starting at this node. Okay, so the first algorithm we're going to be looking at is a depth first search. And the core concept is exactly what the name implies. We're going to prioritize depth when we're choosing the next node to visit. And in this algorithm, we're going to recursively visit the neighbors of a node. So let me draw a simpler version or simpler graph to represent DFS. So I'm going to draw several nodes, and this is just to illustrate the idea of DFS, and we'll go over one more example after this. So I'm going to draw undirected edges going through these nodes like so. Okay, so let's say that we start at this node. So this node at the top. And let's pick a neighbor from this top node to go to. So let's say we pick this one. So it's going to go along this edge. It's going to go along this edge, and it's going to visit this node right here. And once it's here, the idea of DFS is we're going to now look at the neighbors of this node. So the neighbor of this node is this node. So we're going to go down, and same thing. We're going to visit the neighbors of the node, this node, and all the way until we reach a node that doesn't have any unvisited neighbors. And we'll come back, and then we'll try another neighbor with this. So let's say this time it goes towards the right. And we're going to look at the neighbor going towards the right. So for this one, the only neighbor unvisited is going down. And again, we're going to go down from here. And once it's run out of nodes to visit here, it's going to come back up and then go down the edges like so. And so this is how a DFS could work. And obviously, depending on how your adjacency list is iterated through, it could be traveling down this node first. But the idea is you pick one side, you go as deep as possible. So as deep as possible. And once you've run out of nodes, and that's when you pick another neighbor, and then you go deep as possible again. And so that's the idea of DFS. Okay, so now let's think algorithmically. So how would we make an algorithm that kind of simulates this? So you can see that the process of repeatedly going to your neighbors, that's kind of recursive. So starting from one, let's go through the adjacency list at one. So let's assume that we're starting here. So we're starting at one, and we go through the adjacency list. So that's 6, and we go to 6. Okay, that's fine. So by calling, let's call our function DFS. So DFS at 1 is our first call. So that's when we are at node 1. And once we see this adjacency list has a 6, so that's 6 is a neighbor of 1, then we call DFS at 6. So then by using DFS at 6, we are now at node 6. And now we look at the adjacency list of node 6. And so the neighbors of node 6 are 1 and 5. So 6 can go to 1, 6 can go to 5. And now we see a problem, because if I choose 1 to go to here and I call DFS at 1, what that's going to do is it's going to call DFS at 1. And after we call DFS at 1, 1 is going to look at the adjacency list and go to 6, and 6 is going to go back to 1, and so on, right? So if we're allowed to go back to node 1, then our recursion will never stop. It can just keep shuffling between the two nodes. So it can go from 1 to 6, back to 1, back to 6, back to 1, right? So that will cause a problem for us if our recursion doesn't stop. So earlier we mentioned that it's going to give us the recursion error, max recursion depth exceeded. So how do we solve this problem? So we can avoid this by keeping track of whether we've already visited a certain node. So let's define an array. So an array is same as a list, basically. And let's call it visited. And if where node u is visited, if node u has not been visited, then we're going to say visited at u is equal to false. And if visited at u is equal to true, then that means it has been visited. So false if it hasn't been visited, and true if it has been visited. And now how we can use this is that, first of all, whenever we arrive at a node, we say that it's visited. And whenever we go through the adjacency list and consider whether a neighbor should be visited, we're going to ignore the nodes that are already visited. So now using this visited array, but here's a possible traversal of the graph using depth first search. So again, I'm going to start at node 1. Now, obviously, you can start at any node you like. I just picked 1 for simplicity. So let's start at node 1. So immediately when we arrive at the node, that's not a great underline. So as soon as we arrive, we're going to mark it as true. So in my drawing here, I'm going to just cross out a node. I'm going to circle a node if I'm currently visiting it, and I'm going to cross it out if I marked it as visited. So as soon as I get here, I mark it as visited. And so I mark it as visited, and I go to node 6, because the adjacency list at 1, it consists of 6, right? So I call DFS at 6. And so now that I'm at 6, I immediately cross it out, and that means I mark it as visited, right? So visited at 6 is equal to 1. So these are the calls I'm making. Visited at 1 is equal to true. Visited at 6 is equal to true. Right. So that's what I mean by like crossing it out like that. So now that I'm at 6, I go through the adjacency list of 6. Okay, so that's 1 and 5. So now when I go through them and I consider 1, I see that 1 is already crossed out because, excuse me. Because I already marked it as visited. So what I do here is that I ignore it. And I move on to node 5. So node 5 has not been marked visited. So initially we're going to mark everything as false because nothing's been visited yet. And we're just going to call DFS at 5 from 6. Someone's mic is muted. I don't know if that's okay. So anyways, now that I've arrived at 5, I immediately mark it as visited. So then I look at the neighbors of 5. So that would be 3, 4, 2, and 6, right? So 6, 2, 3, 4. Okay, so I look at 6. Is 6 already visited? Yes. So ignore it. Is 2 already visited? No. So I can go to 2. So let's say DFS at 2. And so I'm going to go visit 2, and I'm going to cross it out. And that means that 2 is already visited. So now I look at the adjacency list of 2. And that's going to consist of only 5. And now when we I need to move this zoom in. Okay. Now when we look at 5 and we see that it's already visited, there's nothing left in the adjacency list for us to visit, right? So that's when we reach our, you could call it a base case, or a case where the recursion stops. So in this case, once we've reached 2 and there's nothing it can visit it that hasn't already been visited, then no recursive calls are made here. So no recursive calls are made from node 2. Okay, but we're not done with 5, right? After we're done with 2, we still have to go to 3. So is 3 already visited? No. Okay, so we're going to go to 3. So DFS at 3. Okay, that's not a great drawing, but just pretend that's a 3. But yeah, so we're going to arrive at 3 and immediately mark that as visited. So now let's go through the adjacency list at 3. So that would be 5 and 4, right? So looking at 5 and 4, 5 is already visited. 4 is not visited, so we can go to 4, right? So we can go to 4 and say DFS at 4. And once we go there, we're going to mark it as visited immediately. Okay, so now that it's visited, let's look at the adjacency list, and that'll consist of 3 and 5. Is 3 visited? Yes. Is 5 visited? Yes. And again, we've reached a case where everything that, where all its neighbors are already visited. And that means that no recursive calls will be made. Okay, so now we're still not done with 5, right? We've visited 3. From 3 we went to 4, and from 4 we stopped. But now we have to go back to 5 and look at 4. So is 4 already visited? Yes, it actually already is. So we ignore it. So before we visited 3, 4 was still unvisited. But after we visit 3, 4 is already visited. So this is a case where visiting 3 also visits 4. So you would ignore it. So this means that we have to do a check for every single node as we're looping through the adjacency list. Okay, so are there any questions about the simulation of DFS? Okay, so if at any point you have any questions, remember that you can always type in chat or unmute to ask. Okay. So let's look at the Python implementation for depth first search. Okay, so we have our adjacency list. You can go and check that this adjacency list is correct. So this adjacency list should correspond to this graph that we have. So first of all, as we said, we're going to initialize a visited array. So initially everything is false. And so the reason that we multiply this by 7 instead of 6 is that we have 6 nodes in the graph, and lists are indexed from 0. And so that means that since 0 will be a dummy node, we're going to need a list of length 7 so that we can access visited at 6, right? So initially, everything is false. So if you're wondering what visited looks like, it's just an array of false, right? So false, 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 false. Okay, so that's what visited is. And now we can start doing our DFS. So now that we have our adjacency list and our visited list. So this is the depth first search, and this isn't part of the algorithm. I'm just printing out what node we're visiting so we can see what's happening in the function. And so as soon as we get to node U, so whatever U is passed into, we're going to mark visited at U to be true. So mark node U as visited as soon as we get there. And now we're going to go through the adjacency list at U. So remember that we constructed the adjacency list so that adjacency list at U will give you all the neighbors of U. So here we're writing a for loop to go through its neighbors using the adjacency list. And now we're going to perform a check. So if not visited at V, so this will be satisfied if and only if visited at V is equal to false, right? So make sure the neighbor isn't already visited, and then we're going to go visit the neighbor. So we're going to recursively call DFS again. And so this is where the recursion takes place, right? So in the definition of DFS, we're calling DFS. And DFS at V, we're going to go visit the neighbor. And finally, we're going to start the traversal at 1. And so DFS at 1. And if we run it, we're visiting node 1, then 6, then 5, then 2, then 3, then 4. And if you remember, this is exactly what we had here. So we visited 1, 6, 5, 2, 3, and 4. Yeah, 1, 6, 5, 2, 3, 4. So this is the implementation of DFS and Python. Are there any questions about the implementation?
And before we continue, I sent the workshop code in the chat, just in case you guys haven't attended the previous workshops. The workshop code is like a token that you can input where you can get points because you've attended the workshop. So either on the Discord, in the Discord right now, in the bot channel, type /code and then the token to redeem your points, or do it right after this workshop because the points do have an expiry time. Yeah.
Okay, so if there are no questions, I'm going to start talking about another search algorithm, and this is what we would call the breadth first search, and in short, it's BFS. And as we named the function here, depth first search, in short, is BFS. So BFS is another algorithm to traverse graphs, and the core concept is to prioritize breadth when picking the next node to visit. So in other words, we're always going to try to visit the node that is closest to the source, and the source is the node that we started at. The reason I use that graph at the beginning for DFS is that I want to try to compare that with BFS. So I'm going to draw the exact same graph structurally. So our graph, when I demonstrated DFS at first, looks something like this. Okay, so this is our graph. And we're going to start our BFS traversal also from this top node right here. So it's always going to prioritize breadth. So that means we pick the node that is closest to the source. So these are equally close to the top, so it doesn't matter which one we pick. So let's just pick the one at the right this time. So it's going to go to this node. So this node is already visited. Okay, so now let's pick the next node to visit. Now in DFS, you would have taken this node and visited its unvisited neighbor, which is right here. But when I mean closest, or in terms of distance, I mean the number of edges, right? So if we were to visit this node, that would not be BFS anymore, because let's look at this node. So this node is also unvisited, and its distance to the first node is just one edge. But this node has a distance of 2 edges from the source. And so we can't be visiting this node, right? We have to be visiting those that are closest to the source. So when we pick a node to visit, actually, I think I should write down the distances to the source beside the nodes. So these have a distance of 1. these have a distance of 2, and these have a distance of 3. Right? And we're assuming all of these edges have distance 1. We're dealing with unweighted graphs today. So hopefully it's clear why. So there's one edge going down here, 2 edges going down here, 3 edges going down here. So that's how I'm assigning the distances. It kind of looks like 10 and 20 and 30, but these circles are just circles. They're nodes, they're not zeros. So anyways, we want to pick the nodes that are closest to the source. So before we visit anything that has distance 2, we have to finish visiting those that have distance 1. So we can pick another node like this one. So then we only have one choice left. We can't pick any of these, right? We have to pick the one that's closest to the source, which is this. And in some order, we have to pick the ones now with length 2. And since there's nothing with distance 1 left, so we would visit maybe this, this, and this. And we would visit this, this, and this. So in DFS, what we did was we visited one tree or one branch, and then we visited this branch entirely, and then we visited this branch entirely. In BFS, what happened was we're visiting this first, then this, then this. Then we're visiting this, then this in some order. Then we're visiting maybe this and this and this in some order. So it's always going to go from the closest to the furthest. So are there any questions about this example? If you have questions, I think I said this, but you can always type or just ask. Okay, so let's look at another graph. So here again, I'm going to start my traversal at node 1. And the idea of breadth first search is that we want to visit all the neighbors of 1 before we visit any of the neighbors' neighbors. So in this case, we will first visit 2, 7, 4 in some order before we go and visit other nodes. And that's because 2, 7, and 4 have the distance of 1 with 1, right? So one edge, one edge, one edge. Okay. So for example, node 3 will never be visited before node 7. But this can happen in DFS. So in DFS, if I go from 1 and go to 2, then go to 3, then I would visit 1, 2, 3 in that order. But in BFS, since these have length 1 and 3 has length 2, there's no way I'm going to visit node 3 before node 7. Okay, so the question is, how will we know to visit node 7 and node 4 after visiting node 2? So if we were to use recursion and we ended up at node 2, how do we know that we want to visit node 7? Because 2 has no edges to 7, right? If you go through the adjacency list at 2, it's not going to tell you anything about 7. It's going to tell you that the neighbors are 3 and 1. So instead of using recursion, we will use something called a queue to store the nodes to be visited. A queue is an ordered list of objects in order of when they were added. And the objects are extracted from the front and added to the back. And the logic is very similar to a line at a cashier. So the person who lined up first is at the front of the line, and they reach the cashier before people behind him. So we can implement our own queues, but it's easier and probably more efficient to import the queue object from this Python class. So you can go to this link and look at all the functions here. So what we're interested in here is class queue.queue. And it has a lot of functions here, but today we're mainly going to be focusing on 3. So let me just demonstrate what queue does. So to use queue, I'm going to say from queue import queue. So, and then I'm going to create an instance of queue. So I'm just going to name my queue the letter Q, just because it sounds the same. And I'm going to say Q is an instance of a queue. So Q is equal to Q. So now my queue is a queue. So the way you print out a queue, in case you ever have to debug your code, or in case you want to find out what is currently inside of your queue, if you try to do something like print queue, it's not going to end very well. This is not very useful to you. So instead you do q dot q, and that's how you're going to get what's currently in the queue. And we'll be using this to demonstrate later. So the way you add something to a queue is you say q dot put. So I can say q dot put 3, and I can then print q dot q. And let's run this. You can see that before it was empty, but after adding, we added a 3. And we can put some more things in there. So q dot put 5, q dot put 7. And you can see that we have 3, and then we added 5 and 7, and 5 and 7 are going to be behind 3. And so they're going to be ordered in the order that they were added. And the way we extract something from the queue is we say q.get. So that's going to take whatever is at the front of the queue and give us that value. And not only is it going to give us that value, it's also going to extract it from the container. So if I do print q.q again, after 3, 5, 7, we said q.get, so that gave us 3, and now we're only left with 5, 7. So you can imagine that we have some list of numbers. Maybe we add 1 to the queue, then 2, then 3, then 4. Then we extracted 1, then we extracted 2, then we add 5, then 6. So I'm always adding the numbers towards the back and taking the numbers from the front. Is this clear? Does anyone have questions about queues and how we use them in Python? Okay, so one final function that we're going to use is the q.empty. So q.empty is simply going to return whether this queue is empty. So you can see that this queue has 2 elements in it, so it's definitely not empty, and that's going to return false for us. But if we instead say maybe we say q.get again, q.get, and then print q.q. Then our queue is going to be empty, and now let's print q.empty. And that's going to give us true, because the queue is now empty after extracting 2 elements. Okay. So again, we're going to be visiting, we're going to be using the visited array to keep track of the visited nodes so that we don't end up in an infinite cycle, right? So because this can still happen. But this time we're going to mark a node as visited as soon as we add it to the queue. And so this way we won't be adding the same node into the queue twice. Let me give an example of this. So let's say our graph is very simple. It only has 3 nodes. And it has undirected edges like this. And we start our traversal from here. And it's going to randomly pick a node. These both have distance 1 to this node, so it's going to visit here, right? But these both get added to the queue. So I'm going to add this to the queue and add this to the queue. So instead of this and that, I should probably name them. So this is 1, 2, and 3. So our queue becomes 2, 3, right? 2, 3. In the case, if we don't mark 2 and 3 as visited already, then our visited list would only have 1 as visited. So then now that we go to 2, it's going to extract the 2, so it's going to be left with a 3. And then 2 is going to look at its neighbors. So if it looks at 1 and 3 and it sees that 3 is not visited, it might just add the 3 back into the queue again, right? So then if it extracts the queue, or hold on, I think. Yeah, so okay, actually this example doesn't work very well, but just this is just an optimization that you can use with queues. I can't prove it right now on the spot, but yeah, this is just how you implement BFS. Without it, the algorithm would still work, but in if I remember correctly, it's less efficient for some reason, but I can't think of it right now. Okay, so at the start of the algorithm, we're going to put our starting node into the queue and mark it as visited. And as the while loop runs, we're going to repeatedly extract the nodes from the queue to visit and add their neighbors into the queue and mark them as visited. And when the queue becomes empty, we know that there are no nodes left to be visited and our traversal is finished. So let's look at a possible traversal of this graph. So I think it would be helpful if I check this graph and just placed it right afterwards. So that's clear. Okay, so we're going to start from node 1. I'm going to start here. And before 1 is added to the queue, it should already be marked visited. So our queue was empty, or it had 1, and 1 is visited. And now that we are at 1, so the queue, we extract 1 from the queue. So now we add its neighbors to the queue. So 2, 7, and 4. Now the queue looks like this, and I just realized that example does work, and that was why, but I'm not going to go back to that. Okay, anyways, so 2, 7, and 4 are all added to the queue now, and as we said before, as soon as we add it to the queue, we're going to mark it as visited. So these are visited, even though we're not extracting the nodes from the queue yet. We're going to say that they're already visited. So now let's just pick the random node in the queue, or actually, in this case, if we add them in the order of 2, 7, 4, we're going to take 2 first. The queue becomes 7, 4. And we're at 2. So 2 looks at its neighbors. So it looks at 3, and it adds it into the queue. So this is, again, we're still using a visited array, so it won't go back to 1 and cause an infinite cycle. So it goes to 3. And that marks 3 as visited. So if we add it to the queue, and remember, we're always adding to the back of the queue. And if you imported the queue object, it automatically does this, so you don't have to worry about extracting from the front and adding to the back. So it adds 3 into the queue. So then we look at the next node in the queue. So we no longer look at the neighbors and then immediately go visit the neighbors. We instead add the neighbors to a queue and then look at the queue to see which one should be visited next. So then the next node in the queue is 7. So our queue becomes 4, 3. Okay, so at node 7, we look at the neighbors. It has no neighbors to visit that aren't already visited. So we look at node 4. So we take node 4. So the queue becomes only 3 now. So then we look at the neighbors of node 4. So 1 is already visited, but 5 is not. So 5 gets added to the queue. So 3, 5. So 5 becomes visited. And the next node in the queue is 3. Okay, so now that we're at 3, it looks at its neighbors and it doesn't find anyone that's unvisited. So that just ends there. And we take 5 from the queue. So we're at 5 and we look at the neighbors of 5. So that's 4 and 6. 4 is already visited. We ignore it. So then we go to 6 and mark 6 as visited as well as add it into the queue. So now the first node in our queue, that'll be 6. So we take it from the queue and we visit it. And then when we look at the neighbors of 6, everything is visited. And so we add nothing to the queue. And so our queue becomes empty. And we're going to have a while loop checking whether the queue is empty. And as soon as the queue becomes completely empty, that means that every single node in the graph has been visited. And keep in mind, our graph is connected always. So if there won't be a random node out here that you haven't visited. So now that the graph or sorry, now that the queue is completely empty, when we check it, all the nodes in the graph are visited. And so are there any questions about BFS? Okay, just in case I confused anyone earlier, so the reason we add these nodes into and the reason we mark them as visited as soon as we add them into the queue. So again, we have 1, 2, 3, and if we go to 2, so we're gonna put 2 and 3 into the queue. We're starting at 1, and then we mark 1 as visited, and then we go here and we put 3 into visited. So then our queue will contain 2 copies of 3. And that, to us, 3 algorithm would still work, but having 2 nodes, 2 of the same nodes in the queue is not very efficient and also unnecessary. And so that's why we're marking the nodes as visited as soon as we put them into the queue. Okay, so sorry for the confusion there. Okay, so if there are no questions about how it works, this graph is up there if you want to go reference it. So everything is nicely formatted. I'm gonna delete it. So this is the graph that I did right there. Okay, so let's look at a Python program simulating breadth first search. Okay, so first we have our adjacency list, and you can verify that this adjacency list corresponds to this graph. And now that we have 7 nodes, we're going to make our visited list false times 8, and it's going to look something like. So it's going to be a list of 8 falses. Okay, and as before, we're going to import our queue, and we're going to create a queue, and we put the node 1. And as soon as we put it into the queue, we mark it as visited. Right? So visited at 1 is equal to true. So while the queue is not empty, so keep going until there are no unvisited nodes left. I'm going to say u is equal to q.get. So u is what I'm going to name the current node. So I'm going to extract it from the queue, and then I'm going to print that it's visiting this node, which again is not part of the algorithm. I'm just showing what's going on. And for each of its neighbors, if it's not already visited, first of all, put it into the queue, and second of all, mark it as visited immediately. So you can see that we visited node 1, 2, 7, 4, 3, 5, 6 in that order. Here it's also 1, 2, 7, 4, 3, 5, 6, as we showed before. Okay, so this is, and I can also print out the queue whenever we reach a node. So I can print q.q. Oh, supposed to be brackets there. So printing the queue like this lets you see what the state of the queue is at each step of the algorithm. So at first it's 1, then there's 2, 7, 4, and we keep extracting until it becomes empty. Are there any questions about the implementation of BFS? Okay, if not, here's the exercise I want you guys to work on for the next 10 minutes, and you can take a break. So there's going to be a break from 4 to 4:30. So that's when you're going to take a break and possibly work on the exercise if you wish. And so the exercise is, I want you guys to make an adjacency list by asking the user for the number of nodes and edges, And for each edge, you should ask them the two nodes that they connect, and try to implement DFS and BFS on your own to traverse the graph received from the input. So, and then you can refer to my implementations if you need help. So whenever you get stuck, just feel free to look at these and see how they're done. And finally, there's a bit of a challenge here. So you can ask the user to input two nodes and output the minimum number of edges between the two nodes. So that's the length of the shortest path between the two nodes. And this is a little bit more challenging, so don't worry if you can't solve it fully. Your output doesn't need to be a specific format, and you can make some assumptions about the input format if it helps you. And we're going to take up the exercise at 4:30. Okay, so yeah, so go ahead and work on the exercise if you don't have any questions. And I think I'm going to end the meeting here. So see you at 4:30.